leverage your privileges to the next user. So basically we try to hack a particular binary and we can just try to evaluate our users, right? So now if we check, so binary exploitation occurs mostly because of buffer overflow attacks. So before understanding that, we should know that how the L file gets loaded into the memory. Okay. So for that, I'll just open my audio is not clear, I guess. Yeah, so the EP is saying in chat section that we need to take the control of AIP or API. Yeah, it is correct, but I'm taking this session for beginners, right? So please make it contribution. Okay. So I'll just explain you how the exact stack works. Okay. So whenever we have the program, right? So assume we are using the operating system Linux. Okay. So over here, whenever we try to solve a CTF, one challenge is provided to us. So let us assume the challenge name is chal.l file. Okay. So now this L file is being loaded into the memory, a process. Okay. So this process then, so there are many parts for this process, right? So there is the most high address for this and the most lower address for this. Okay. So now in this process, there are some main parts. Okay. So I'll just cover up it. So the first one is the application part. The second one is the heap. The third one is, libraries. Fourth one is step. So combination of all these forms a particular process into the memory. So whenever we double click or we just try to run the particular file, right? So so these are the main part which get loaded into the stack. So today we're going to focus only on the part called stack because most of the vulnerabilities occur through this part of the program, right? So we'll focus on the stack. So there is a part over here of stack, some memory region which is allocated. The stack is the fixed size. Okay, if the stack size is full, then we cannot try to allocate more data on it. Okay, on the stack, and the heap is for dynamically linking. So we can even exploit heap. So there is one concept called heap overflow, right? So we'll going to discuss in other further presentations and all. So today we're going to focus on this stack. So now I'll just draw this stack. So assume this is a stack. Okay, so now the stack is also in the particular way. So the first part is allocated for the .text section, then the other part is allocated for the .data section. Okay, so text section consists of the code. So the code which you wrote, like this L file is also written in assumed in a C file, right? So the C file code is also loaded into the .text section. Okay, so the all ASM code which is been then converted using compilers and all, and the data section is the part we store the data which is of initialized data. So assume that you all have written a C code in which you all have initialized an int x variable. So this int x will be, so this value is initialized, but the data is not been set, right? So x is equal to 0. So this has not been done. So that comes under the data section, and other part is called .bss segment. So over there, the initialized data are been stored. Okay, so this is a part of this text. Okay. Now, so whenever the process get load into the memory, the stack is been created for it. So there are some notations which you all have to take down. Now there are two type of stacks, right? One works on 32-bit mode, another works on 64-bit. There is nothing much changes in both of these. This chooses 4 byte segments, which is 8 bytes address. Okay. So now there are some registers for this. So in 32-bit, there are registers called as EAX, EBX, EDI, EIP, and many others. Okay. But in 64-bit mode, there are registers which are denoted by RBP, RSP, then RDI, RSI, okay, then RIP. So there are many other registers. For an example, if you want to learn more about registers, you can go to Chromium Docs over here on the homepage of this and just click which architecture you all want to look. Just click on this, and then you will see the architecture. So there are RAX, RDI, RSI, R10, R9, R10. So basically these are registers. So registers are temporary variables in which we can store the data during the runtime of the code and all. Okay. So yeah. So now we know that there are 32-bit addresses, 64-bit addresses, and yeah, registers. So now we're going to take one challenge from one CTF category which I have created. Okay. Let me just exit this. Okay. So I've created one challenge called red to win. Okay. So when I just try to run this while it is asking me some data, enter data. So I can just enter it like hello, right? As a normal user, you will going to enter this, right? But now we need to exploit this binary and take a code execution. Okay. So basically we want to get a shell through this binary. So now I'll just try to show you the code of this binary. So as you all can see over here, I've created a code for it. So basically it is trying to include some header files, then standard library files. And then if you all see clearly, like if you have worked on some, C programming concepts and all, the execution of code starts from the main function, right? So in the main function, I've allocated a buffer array of size 10. And then I've called the putS function to print the that input type, enter data, and then I'm getting it using the getS buffer function. So now I enter the data over here, and then it get loaded on the stack. Okay, and then I get the exit because there is no other further functionalities for it, right? So if you all see, there is one more particular function called bin function, right? And in the bin function, we are trying to execute bin/sh. So if you all know bin/sh, so it is basically a shell command, right? So if we even type it on a terminal, we will get a shell. So now, yeah, if we normally try to run this code, we are not getting the shell because I have not called the bin function in the main function, right? So now we're going to exploit a vulnerability called buffer overflow. And using that vulnerability, we're going to execute the bin function, and from there we'll get a system shell address. Okay. So before learning how we can exploit it, there are some concepts which should be noted by you all. Okay. So first we're going to see what is exactly the buffer overflow. Let me just clear this out. So assume there is a stack, okay, as I've explained here. So there is a stack, okay, and over here I've written that C code, right, of main function. Or I'll just open with the one. Okay. So don't worry about this. I'll explain you what is it. So in the memory, when we try to load that red to win file, okay, we are trying to allocate one stack for it into the memory. Okay, we are trying to allocate one stack for it and on this stack there are some assembly instructions which are running. So whenever I try to compile that ret to win.c file, so it get converted into the object file, and then it is loaded into the binary, which is 1 zeros and 1s, right? So that object file, it is nothing but there is an assembly code for it, assembly code. So if you are familiar with some reverse engineering techniques and all, so in assembly there are some certain instruction and all, right? So as I've explained you all about the registers and all, so these are the instruction: push, move, sub, lean, move, call, and read instruction. Okay, so push instruction pushes the value of RBP on the stack. So now we are trying to load this RBP on this stack, right? So we are just trying to push that RBP on this stack exact. So at the initial position, RBP will be over here. So now why RBP? Because it is 64-bit binary. If it was 32-bit binary, there will be EBP. Getting it? So at the first, we see that we try to push RBP on this stack. Okay, then after the next instruction, we are trying to push RSP at the same value of RBP. So now RSP will be at the same position. Okay, so these are the two main stack registers. Now these are responsible for alignment of the stack frames and all. So whenever the code jumps from the main function to another function called as puts function, so the base pointer and the stack pointer are responsible for the starting of the function and the ending of the function, right? So make sure to note down this also, right? So now after moving the both RBP and RSP on the stack, so now we need to allocate some data, right? So we have allocated the character of buffer of size 10, I guess, yeah. So then the RSP is trying to minus it. So if you all know sub instruction, it minuses the RSP with 0x10 instruction. So now this will grow from upwards, right? So the 0x10 bytes will be allocated on the stack RSP. So now the RSP will be going to point it over here. RSP, okay. So now after the RSP is been pointed over here, so this address, so this part of the stack will store the address of RSP, which is called as stack pointer. Okay, so this part is called as stack pointer, and the RBP will remain over here only, and this part will be having base pointer. Okay, so over here there will be the address of RSP, so it will be in the hex format. Okay, now after that there is one more 8-byte reserved. Okay, so after that there will be one more 8-byte reserved for RIP. So now RIP is the main part of this exploit. So RIP stands for instruction pointer. So this pointer is responsible for loading the next instruction onto this stack. So after subtracting this part of the stack, like after allocating these 10 bytes, so what will be the next address? So next address is 041164. So that next instruction will be loaded over here. So 0x401160. So now the program knows like where to jump on the next instruction of the stack. So this holds the actual value of the instruction which should be executed next. Okay, so now over here the vulnerability actually lies. So now there are actually two parts of this text, two parts. So before moving on that, I just want you all to just know about the stack protections, right? So now I am having this binary called red to win, and it is printing this data and taking the input. So now to check the protections of the file, any type of file in the pawn challenges, there is a tool in Linux called as check sec, okay, and then you need to specify the --- file argument, and then you need to give the argument that file name. So I want to check sec the return to win, red to win file, okay, and then just hit enter, and then you all can see there are some of the stack protections over here. So we'll be not focusing on the relo, the partial relo. We're going to focus on the stack, nx, and pi. So now what is stack? So the stack protection has been disabled over here. So I'll just explain you like what is no canary found, right? So over here, whenever we try to enter a particular amount of data over here, okay, data. So before the instruction pointer, let me drop one more step. Before the instruction pointer, this is buffer size 0x20 bytes. Then there is a RSP, and there is RIP. Okay, so before this RIP, there is a particular one more address segment allocated for canary. Okay, so this canary, if this is disabled, like if this canary is not found, we can just try to enter large amount of data, and it can be overflown on RSP and even on RIP. So the stack canary is been disabled. If the stack canary was enabled, whenever we try to enter the large amount of data, right, so it will get overwritten on the RSP pointer and even on the stack canary. But the stack canary will not allow us to write more data onto the instruction pointer, because in stack canary we check the initial value of the canary. So whenever the program get executed into the memory, a stack canary variable is been set to a randomized int canary is equal to randomized. So this randomized value is being set to the canary. So canary only knows that. So assume that this value was like 7F02C000. Okay. So if this value is not matching to the initial value, right? So whenever I try to overflow the buffer, including the instruction pointer, right? So it will not give me the execution to write the address on the RIP, because this stack canary will going to get mismatched and the program will going to execute it as normal. So it will going to exit the program. So this functionality is called as stack canary, right? So now I have disabled this because we are trying to solve a CTF problem. So now there is one more stack protection called as NX. So NX is enabled over here because we're not going to use the NX, okay, the stack protection. So now what is NX? So NX is non-execute bit, exif bit. So whatever we try to load onto the stack, okay, inside the buffer, whatever we try to write. So like if our malicious attacker tries to write something malicious code, so that malicious buffer will should not get executable permission. It should have only read permission and write permission, not X permission. Getting it? So non-executable bit is set to be on. So whatever we write on this stack should not get executed. Okay, so that is called as NX. Now there is one more third protection, which is the most main protection to solve this binary. So this is no pi. So what is pi? So pi is basically a position independent executable, okay, pi. So every time we try to load this particular file, red to win file, onto this stack, right? So whenever we try to load that file, their addresses will not get changed. So addresses within the binary are going to remain same. It will not going to get changed. So this can be helpful while jumping from one point to the another point, right? So what we can do is that So now, as we all know that this was a stack layout, right? Some attack factors. So now we're going to perform one particular attack on this manually. Okay. So I'll just go here. Till now, anyone is having doubts, so you all can just tell me. I was a bit fast, I know. This was my first session, so
Hello.
anyone is having doubt? Yeah, yeah,
So for example, if we input like 1,000 characters, the
yeah,
canary
yeah,
value will be changed, right?
yeah, yeah, yeah,
So where is the program checking that the value is changed? Because
yeah.
I've stored from the stack, so there is no way
Yeah,
like.
yeah. So for that, we need to compile two binaries. So I'll be going to show you that also over here. So if you also have opened some two challenges over here. So this is red to win challenge. So I've just named it. So if you all see over here, I've decompiled it using Ghidra. So Ghidra tool is most useful for binary exploration categories and even the reverse engineering in most of the parts. So if you all see, I've compiled this binary without some stack protection. So as you all can see, it is basically just trying to allocate the 10 sides of buffer and taking the input, and over here it is not checking the stack canary, right? So I've compiled one more binary with same code, but with some stack protections. So as you all can see, it is checking over here. The initial value should match the previous value, right? So if the match does not perform the correct, like if the match is not same, the program is getting the stack check fail error. Are you getting it here? I hope this was your issue, right?
No, no. See, the stack check fail is checked here, right? But
Yeah,
after when I enter a long data,
yeah.
it also overflow the this stack check fill function.
Yeah, but it will going to exit the program because the initial value is not matching the initial value of the stack canary. So it will going to exit the code.
Yeah, where is that initial value stored?
It is been got using the runtime function, and also basically it is a very deep part in this code. So if you can see, there is one allocation for long in offset and one long 10 variable, right? So over here there is one allocation, as you can see, long 10 is equal to in offset plus 0 100. So this value gets randomized and then it is stored onto the stack, and if this value is not matched to the initial value, then it will going to exit the function. So basically over here you can see this line is the most important line when we are enabling the stack canaries and all. Is it clear or should I go?
Yes, yes.
Yeah. So now in this way we can check the stack canaries and all. So now if you all are creating some your own challenges, right, then I'll just show you how to compile this. So as you can see, we are having the red to win file. So if I want to compile, like if I want to disable all these stack protections and even canary, so there is a command gcc red to win red2win.c. So first we need to specify the name of the file, the C code file, and then -o stands for output of the file. So where I want to store that output in which format. So red2win only. Then -f no stack protector. So if I pass this tag or this parameter, so this will going to disable this stack protector. So basically this will not going to check for this. So this functionality will be disabled while compiling the code, and you will get the code in the form of like this. So stack protection will not be going to check. So this is the way. So -f no stack protector and -no pi. So -no pi will just the addresses inside the binaries will going to remain same throughout the code. So and then if you hit enter, then it will definitely show some warning of get test because these functions are vulnerable to buffer overflow. I'll just discuss some what other functions are also vulnerable to buffer overflow in the last part of the video. So after compiling this, I'll get a file, red to win file, and if I just run the check sec, so this will be the same, right? So now if I want to get some of the files without stack protection, right? So I've also created that also. I'll just change my directory. with protections. So as we can see, we are having the same file here. So I've just changed the name, no issue. So check sec similarly with the char. Okay, and if I hit enter, so we can see canary also is found, and x is also enabled, and pi is also enabled. For that, the command is very simple: gcc, then char dot c hyphen o, then the name of the file, and then hyphen enable the canary part. So there is a command for it. I always forget that command. Hyphen f stack protector. So this will going to enable the stack canary. Okay. So again, it will going to show me some warning. So because getter is going to buffer overflow, and if I do check sec, you can see canary is also found, and x is also enabled, and pi is also enabled. Okay. Now, before moving to exploit, let me go to that same directory. So yeah. So now anyone knows like why did I name this binary red to win? Are you all getting some hints? Okay, so let me tell you all. So we're going to exploit this binary, and we're going to write the address of the win function on from the instruction pointer. So every time we try to enter the data, after we enter the data to the instruction pointer, we're going to write the address of win function, right? And from there we'll going to get the code execution, because in the system function we are passing win sh. Okay, so for that we're going to use some Python tools, right? So there is a Python library, so it is most famous in pawning the challenges and all. So I've already created the script for this. Okay, so I'll just have a walkthrough through this. So whenever we try to import some models in Python, we use this syntax from pawn import star. Okay, and then we are trying to set the context.log level to debug. So whenever we want to debug the particular file and all, right, whenever we are trying to solve some challenges or some methodology, so we need to debug it. So we can say the particularly that how many bytes are going into the program, or how many bytes are being received from the program. Okay, so after that we are setting the elf binary over here. So it is elf is equal to context.binary. So we are initializing both the values at the same is equal to elf, and then we are passing the first argument as red to win. So this red to win will be your targeted binary to get load while solving the challenge. And then we are passing one argument called check sec is equal to false, because every time you run binary you will get this kind of output. This one, it was check sec, right? Yeah, so every time you run the binary you will get this output over here, and we don't want it, but if you all want it, then you all can just remove this. Okay, no issue. Now the main part comes into the payload section. So what will be the payload will be going into the memory of that C code, and it will going to manipulate, and we can get the shell access. So before moving to payload, we'll just try to see what are offsets. Okay, so now for binary exploration category, there are many tools in Linux like IDA and all, but for debugging there is a most famous tool, GDB or radar. I mostly love working on GDB because with some pawn debug extension. So if I do GDB, and then we need to specify the name of the file, so it is red to win, and I hit enter. So this will going to pop up with the the UI of pawn debug. So pawn debug I recommend for even for beginners to try this, because this has the a lot functionalities which will help you all for further exploitation categories in the form of binary or pawn challenges, right? So now there is a command called as info functions, right? So info functions, info functions. So info functions will give you all the addresses of all the functions present in that binary, right? So these functions we have not returned it. So now these functions are by default has been added by the compiler. Okay, so we will not focus on this, but these two functions we have written it, right? So these are also been loaded onto the stack. Okay, so the main function is also there and the main function is also there, and this is the function name and this is the address on the stack where the function is now currently at the point. Okay, so now if we want to check the code of the main function but it is of no use, but still we are having the actual code over here. But when you are solving a CTF challenge, assume that you all have because they have only provided you all the L file and they have not provided the code, then you all can do check using the one command called disassemble. So disassemble, now after disassemble we need to give the name of the function which you want to see the code in the form of assembly. Okay, so if I want to check the code of the main function, right? So I said disassemble main, so this will going to dump me the code of the main function. So now if you are familiar with some assembly languages and all, so this might be very helpful for you all. If not, I'm going to explain it some in basic way. So first of all, it is trying to push RBP register on this stack and then move RBP and RSP. So I've also explained it over here, right? Where is this? Over here, RBP, RSP and all. So basically it will do some allocations on this stack. Okay, so after doing that, it is calling the putS function and getS function to take the input. So there is one trick in the pond debug, so you can just take it as a tip. Okay, so whenever if you want to check some strings or hex values onto this stack of the particular binary, what you can do is that you can use a command called x slash. Okay, so x stands for examine slash, and then after we need to specify in which format we want. So I want format in S, so I'll just copy this one particular address from this stack and then just paste it. Okay, so as you can see it is telling me enter data. Okay, so X stand for examine slash S stand for I want the output into the format of string. So now what is this instruction doing over here? So it is so the first instruction is trying to set up the allocation of the stack. Okay, after that there is one instruction called as LEA. So LEA is a type of instruction in 64-bit mode. Whatever we specify over here, so RIP plus at this address, so this whole address, so what data is there from that address, load that particular address into RX value. Okay, load that particular address into the RX value and then move that RX value into the RDI registers. So as I will explain here the about some registers, so you can see, so RDI register is responsible for loading the zeroth element, so we can say it as a first argument into this while passing or calling the function. Okay, so this RDI register has been invoked over here, x slash s. So we can see then after that we are calling putS because putS requires a argument. So we can see inside the putS we have passed the argument in the format of string, right? So that string address should be loaded into the RDI register. So this is the basic part where we should know like how the assembly instruction actually works. Okay, so x slash s, then we try to examine the address. So now the main part is there to find the offset. So now what is offset, right? So I can say it. So offset is a term in which how many data is being required to overflow till the instruction pointer. So from here till here, we know that we require some 10 bytes plus how much data is required to even overflow the stack pointer and jump to the EIP, the instruction pointer. Okay, so that much of data we need until we overflow the EIP. So assume we want to enter the data like A until and unless we try to overflow the EIP. So whenever we reach that the entry bar of the EIP, we can enter our own addresses from this stack and we can get the shell access. Okay, so for that there is a command in JDB only, so it is cyclic, or and then we need to specify that how many bytes you want to generate. So I want to generate around 50 bytes. And now if you'll see it correctly, so it is trying to allocate some 8 bytes, and after 8, before going to instruction pointer, there is a segment reserved for RSP, which is called as stack pointer, right? So stack pointer, so we should find out at which address, exactly at which offset the stack address we can overflow and write it to instruction pointer. Okay, so over here we need to copy the first 8 bytes. So we need to copy the first 8 bytes, because after the 8 bytes, anything which is going on to the address, it is getting overwritten on the instruction pointer. So just copy this 8 bytes. So say cyclic -l to get the offset. Okay, -l is used to get the offset, and then just paste the address. Okay, and then we can see at the 18 byte we are getting the offset. So now even if you want, you can find it manually using like creating like a b b b c c, and also it is also a bit time consuming, but you all can see we have got the offset 18. So after 18 bytes, whatever we write, it is getting overwritten on the instruction pointer over here. Okay, so what we can do is that, so if I say anything, whatever I write onto this stack, okay, so plus 18, so a into 18, so 18. So after 18 bytes, whatever we write is getting executed on the EIP. Oh, sorry, RIP. So instruction pointer. Okay. So now what we can do is that we can paste one address over here of anything, right? So what we can take the opportunity over here is that we can copy the win function address, and we can paste that win function address over here. So now what the execution of code will be, the jump bytes will be going to load it on the stack, and it will then going to jump on the win function. And from win function, we know that we are getting the shell access. Okay, so let us try to do it using pond debug tools. So if you all can see, I've created some, this particular file. So I've explained till here. So in payload section, we have got the offset, right? So the offset is 18. So we send a cycle.
Pratham,
Yeah.
sorry, I'm really sorry. Can I just take 1 second?
Yeah.
Yeah, guys, so we have a 60 minutes limit on this Teams app. So please, I've shared a link in the chat. So go ahead and join that Google Meet link for those who are in the session for the rest of it. Thank you.
Yeah. So now I was on the this function address. So anything which we try to put some addresses on this. So after the 18 bytes, whatever it is getting overwritten on the instruction pointer, and we take this as an opportunity, and we try to load the win function address. And we know that in win function address, from there we can get the shell access, because we know the source code, right? We know the source code. So over here, so we are getting this system/bin/ss. So now without calling this function, we are trying to call it using the instruction pointer. So now the payload section I'm going to explain. So it is sending the until the 18 bytes, and then it is trying to pack one particular address. So now what is pack? So pack is basically it packs into the Little Indian format. So now what is Little Indian format? So anything, whatever you write on this stack, it is getting loaded into the reverse format. So this is the storing way of this stack. So there are two type of it is in Little Indian also, and then Big Indian. Okay, so in Little Indian, if I want to say store some hello keyword, so it will get store as in reverse. Okay,
Hello,
like
Pratham.
this backslash. Yeah, yeah,
Yes. Can you just please join the Google Meet link so you won't be interrupted abruptly in between. I'm really sorry for that, but
yeah,
we're almost going to reach the
yeah,
limit. And yeah, so
yeah,
everyone who's in the session, please join the Google Meet link that was shared in the
yeah,
chat, and the session will be continued there right
yeah.
now.
Okay.
All right. Okay. Thank you, Pratham.
Yeah. Adding some jump value until the 18, we can control the uh, instruction pointer, and we can just write the address of the win function address, right? So I was explaining all this exploit. Okay, so now in the payload section we have already sent it the 18 bytes. Okay, so after that we are trying to send one tag address, so that let me just try to modify this. So I'll just explain what I'm doing over here. Instruction. Okay, so over here we can see that I've did some a bit changes. So now what is basically these addresses, right? So these addresses are from the stack only, sorry, from the particular binary file only. So now what is basically the rat instruction? So rat is return instruction. So this instruction is used while we are trying to jump from the cyclic pattern, or we can say if we want to jump to a certain part of the stack addresses. Okay, so when we are in 64-bit mode, so we need to jump on the 8-bit address. So this is due to the some misalignment of stack. We need to compulsorily jump on some return address, and then we can jump from wherever we want to jump on the stack. So first of all, we are trying to jumping on a normal return address. So now where can you find out this return address? So it is a very easy task. So what you can do is that we can just disassemble the main function. Okay, so disassemble the main, and then we can just copy this rat instruction. So if you open any kind of function like win or main, which is user defined only, okay, not compiler defined, so user defined, so you will find one rat instruction. So you can copy this instruction and just paste it over here. So rat. So whenever we try to override the instruction pointer, there is some misalignment of stack, and we need to always jump on some return address only in 64-bit mode. In 32-bit mode, you can just directly copy the address of the system and jump it over there. Okay, so after jumping on the return instruction, we can jump onto the system address. So for system address to find, we can just do disassemble system. So this is very easy. System. Okay, so and we get this address, so E102, and we just paste it over here. Okay, so I'll just do some exit, and then if we just try to run the exploit.py, we are getting some switching to interactive mode. And if I do some basic command like ls, we can see we have successfully got some remote, or we can say the code execution. So this context.log level debug, so it is just telling me that what data I've been sent. So we can see we are sending the cyclic pattern of these bytes, so until the 18 bytes. So after 18 bytes, it is sending the return address. Okay, the return address over here, and after that we are jumping on the system address, and from there we are getting the shell access. So if I just try to do, so don't display anything, so we can just run this exploit, get ls, so we can do, so we have got successfully, we have got the shell access. Your name -a plus -lh, and then we can do any other stuffs like get some cat etc shadow file, or we can just do cat flag.txt. So in this way we have jumped from one instruction to the another instruction, and we have got the return to win address, right? So in this way we can solve some simple challenges from the picoctf.org. I'll just give a walkthrough over there. picoctf. Okay, so you all can just go on to this link. I hope that most of you all are aware about this website where you all can practice this kind of stuff, and then just click on the binary exploration category, and then just go to buffer overflow 0 part. The first part is over here, I guess. Yes, the buffer overflow one. So you all can solve the challenge from here also. It is a not big task for you all, because the bin function is already been provided for you all onto the that particular binary file, right? So in this way we can solve the buffer overflows using the pawn challenges. So most of the pawn challenges are made using buffer overflow vulnerabilities only, because there are some challenges like in which you'll need to know some format string vulnerabilities and all. So I will just share some links for you all in the chat section or after this presentation, so you all can just go walk through it. So any other doubts you all have till now? Anyone can just unmute their mic and just ask me. Anyone is having doubt or any other stuffs? So we can just do a quick recap, okay? So what we have learned today. So I know it was a bit fast because this was my first session for y'all. So today we have just learned what is exactly the binary exploitation, right? So it is a process of exploiting a system program using buffer overflow vulnerabilities mostly. So then we explained what is exactly the buffer overflow, and then we saw the what is the exact stack layout over here. This is the messy part. And then we have checked the stack layout, so what is process, and from there we have shown the like how the stack works, right? So there's instruction pointer, registers, then all. Then we have saw the attack vector, like the instruction pointer, how we can overflow it and get the particular offset. And from there we have also learned the memory protections and speed pi and all. And then some attacks performed in binary exploitation. So we have performed only this red to win attack. So you all need to practice daily on this red to win attacks from Pico CTF, or even I guess it is present on rootme.org, okay, over there also. And from there you all can perform some basic, okay, red to win and all. And then after making some pro efficiency in that, you all can move to return to libc attacks, then return to shell code, then format string, and then ROPs. Okay, so there are many more lists like heap overflow. Then we can also poison the tcage bins. Okay, so that is a much further part for you all. So for you all as a beginner, I would want you all to practice return to win challenges only. And then the tools used in binary exploration. So these are tools like GDB debugger with pawn debug extension. So if you all use a GDB normal, so it will be not more efficient for you all. You all can just go to this GitHub. Okay, so I'll just try to do here. So if you all just do GitHub and just say pawn dbg, so just go over here and just go to the first link and then just do some git clone. Okay, so it will automatically add that pawn debug extension into your machine on your Linux machine, right? So this was that. And then even Ghidra is also good for analyzing if the source code is not provided from the CTF side. And even the IDA free version is also efficient for solving some CTF. And and if you all want to move like on some other assembles, then you can go it on Cutter and all. So this was the today's session. But still, if you all have having some issues, then you all can ask me, or else we can conclude this session over here.
Yeah, guys. So that was a really inspiring session by Pratham. I think he covered everything really well.
Yeah, but I was a bit fast, I guess, because it was
Yeah,
only
see, this topic actually requires lots of time and
time. Yeah,
dedication. You need to understand what's going on. You can't just take one challenge and see what's happening and then do it for all. You have to really understand what's going in the assembly level, what's going on with the stack and memory, like how Pratham explained it. I think the diagram and all, those explanations were really required and they were on point. So I hope you guys really like the session. If you have any questions for him, please go ahead and open your mics and ask. He will answer them for you. It's fine. Any questions will do. It doesn't matter if you're like, even if you ask what is a binary, you can ask those questions as well. But you should definitely get something out of the session. So if you have anything to ask, please go ahead and ask. If you don't want to open the mic, you can go ahead and ask it in chat as well. It's fine.